Ladies and gentlemen, the floor is yours. 11.3, 11.4, 11.5, the integral test, the comparison tests, an alternating series. What questions do you have? Yes, there.
11.3,
Number 4. So for comparison purposes, do you want to do 3, 5, or 6? It explicitly says use the integral test to determine whether this converges or diverges. But even before I do the integral test, I know I can rewrite this, which means, okay. So I know what the answer is supposed to be. Let's use the integral test to check it. I'm not allowed to just say, hey, this is a p-series, because it explicitly said use the integral test. At which point I'm allowed to say, hey, this is a p-series. So I need to look at the function 1 over x cubed that satisfies the condition that f of n is equal to an, which is 1 over n cubed. And now I need to know, is this function positive, continuous, and decreasing from 1 on? Is that a true statement? Is that a true statement? Now, ideally, I'd like this to be true for x bigger than or equal to 1, but it really only needs to be true for x bigger than or equal to some value bigger than or equal to 1, from some point on. Is that true? Yes. Therefore, the behavior of this series is the same as the behavior of this integral. So now we go through the process of doing the improper integral. One over x cubed is x to the negative 3. The antiderivative then is x to the negative 2 over negative 2. Negative powers go in the bottom. So that's 1 over minus 2t squared minus 1 over minus makes that a plus 2, 1 squared. What happens to that limit? Because that's a 0. By the integral test, since the integral converges, the series converges. And Maddie, yes, this is where I say, yeah, the sentence is what's needed. You have to give me the conclusion. You did a test, what's the result of that test? So in number 4, you know what's going to happen because it's a p-series, but you have to do the work to show me why we know that's true. And yes, later when it doesn't say explicitly, write out all the integral test stuff. Just say it's a p-series and walk away. Leo, better?
Yeah.
Wonderful. More questions. $24. So you want to do 23 or 25 in exchange? So 23 is the sum -1 to the n plus 1 over n to the 6th. And we want an error of less than 0.1, 2, 3, 4 zeros and a 5. Okay, the error is another term for the remainder. So I want to know how many terms I need to add up to get an error that's less than 0.0005. But I know that Rn is less than Bn plus 1, which is the absolute value of An plus 1. Bn's are the positive versions of my terms. So that means I need to know what Bn is from here. Wonderful. So I'm going to set up an inequality. I want 1 over n plus 1 to the 6th to be less than 0.00005. Point quadruple 05 is a fraction. 10, 100,000, 10,000, 100,000. It's 5 over 100,000, right? 5 over 100,000 is 1 over 20,000. The other way to think of it is 0.5 is a half. I have 4 more decimal places. I got to move 4 more zeros. Oh, flip both sides. N plus 1 to the 6th is bigger than 20,000. So all I need is the 6th root. Grab your calculator. N plus 1 bigger than 20,000 raised to the 1/6 power. I don't know what that number is. Where is my calculator? What'd you get, Don? 5 enough? Come back. Thank you. Which means I need n1 to be bigger than that, so I need to be bigger than 2, so I can use 5. If you add up the first 5 terms, you'll be close enough. I have no idea what that total is, but that's my approximate answer. Show that the series is convergent. How many terms do we need to add in order to find the sum to the indicated accuracy? No. How do I know this is a convergent series? Because you'll notice I skipped that part at the beginning, which was stupid of me. I just went right to the error calculation. How do I know this converges? Insert Simpson's noise here. So I really should have done this part first. How do I know that this converges? I can't use that here because this one alternates. But what I can say, well, that's 1 over something huge. That is definitely 0, so I'm good with that. What's the other thing I need to check? So Bn plus 1 is 1 over n plus 1 to the 6th. When you make the denominator bigger, you make the fraction smaller. So it is decreasing, therefore it converges. Again, I have to write a sentence. By the alternating series test, our series converges. An interesting note. The alternating series test only tells us whether or not our series converges. It doesn't tell me that if I fail the series test, that it diverges. It just means that test didn't give me an answer. In the comparison tests, I have a test to see if it converges, I have a test to see if it diverges. In the integral test, the test tells me whether it converges or diverges. The alternating series test only tells me, does it converge? If I fail that test, I don't know whether or not it diverges. I have to use some other method to check. Now that seems weird, because if it's an alternating series and it converges, it should pass this test, but that's not what the test says. The test says if you pass, then you converge, not the other way around. It's not both directions, it's only one. Is the process, if it diverges, I don't get a total, right? Because if it diverges, it's either going to alternate or there's something weird going on, or I'm going to blow up to infinity. So let me give you an interesting alternating series. You'll like this one. One of my favorite alternating series. Sum n equals 1 to infinity minus 1 to the n. Now, if you think about it, this series goes minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, and so on forever. What happens? Well, it fails the alternating series test because the limit then goes to infinity of Bn 1. Right? But that's bounded. If you were to add up every two numbers, what would you get? So here's the fun part. That's 0. That's 0. That's 0. If I add them up by twos, they're 0, right? That's 0. That's 0. So everything after this would cancel out, wouldn't it? Which means the total should be negative 1. But you just told me the total should be 0. How do you mean? I can add it up. I can add it up two different ways. So that diverges, but it doesn't blow up to infinity. It gives me something that doesn't have a logical single total. So by the way, a guy by the name of Abel, Niels Heinrich Abel, in the late 1800s said, all right, if that's so weird, it's somewhere between minus 1 and 0, we'll say that should be minus 1/2. Because half the time when you add it up, you get negative 1, and half the time when you add it up, you get 0. So we'll do a probability thing and say, dude, that's messed up. So there's a whole other way to deal with divergent series that's beyond the scope of this course. So if it diverges, I just walk away from the idea of doing it. If it diverges and I ask you to sum it up, you should hit me with something. Large and heavy, preferably, because that's dumb. Anyhow, the Abel summation theorem is an interesting relation. It would be interesting to find a divergent series that passes the alternating series test. And I don't know of one off the top of my head. I'm going to make a note to that. Is there a divergent alternating series? There shouldn't be. Because not convergent means not passing. But the test isn't enough to tell us that. Or maybe there's a convergent alternating series that doesn't pass the AST. Again, that would make a very weird setup. I got to figure out what the other logic piece of this is. I have a book in my office that is strictly about series because I'm doing a little bit of research on series. For those of you that are interested, there's a poster in the first floor of Lynch talking about this research project. If this series is ideas at all interesting to you, stuff we get to the end of this chapter, I've got a really neat question about, but that's a research project. So I'll look in there and see if there's something more about the alternating series test. Anyhow, I don't want to wander too far from your questions. So ask me more questions. Yes.
11.3, number 10.
Number 10. Oh, okay. Number 10 is just like number 3 and number 4, but it doesn't actually ask you to do the integral, right? It just says, tell me whether this converges or diverges. Number 10 is a p-series. As soon as you write it as a p-series, you can tell me whether it converges or diverges automatically.
Be a P series. Less than 1 for the binary.
Once you flip that, there you go.
This is N3, we can do that in
Exactly. All I need to do is look at the value of p once I've written it in the proper form. I'm done with that one. That's a direct problem. Once I recognize that that really is a p-series. And that's the biggest problem in all of the series stuff, just like it was in all of the integral stuff, is recognizing what type of thing you've got. We'll talk about that more next week. Pattern matching.
28 on 11.4, I'm like confused how to set up the comparison. How to alter it so.
Okay. And I think it's the top part that's giving you the issue, right? E to the 1 over n. So let's think about just that for the moment. I want to think of that like a function for a minute. Does that make sense? What happens when x is small? Right, like if e is 1, then that's just e, right? If x is 1, sorry. If x is 1, that's just e. If x is 2, it's the square root. If it's 3, it's the cube root. What happens when you take the square root of e? I would just say, wait a second, here. There are 2 e's on the calculator. There's the e here, right?
Yeah.
But there's also an e over here. And if you look at that one, it doesn't have a to the x on it, right? So if you want to treat e as a number, you use the 1 over here. So I can do the square root of e this way, or I can do e to the 1/2. Ah, wait a minute. Square root made it smaller. What's a cube root do? What's e to the 1/3? And 1/4? I think it's getting smaller every time, isn't it? So here's my question. What's the limit as x goes to infinity of e to the 1 over x? One over x goes to 0, and then e to the 0 is 1. Okay, wait a second. We start out above 1. We keep getting smaller. We're bounded by 1. Right? So this expression, e to the 1 over n, is always bigger than or equal to 1. Now I have something to compare to. If this is true, what can you tell me about the piece in the series? If this is true, what can you do with the term that's in your series? Now you have something to compare to. Oh, that's sneaky. But I think that is the best part of thinking of series in this way, is that I can stick this in my back pocket and I can go, ooh, I have a P series to compare to. Almost always I'm going to look at a P series or a geometric series for my comparison tests. Aha! Found it. That's a convergent P series, right? Ready? Here's what I want to do. I want to take those and I want to switch the order of every two terms. So I'm going to write it 1/4 plus 1 plus 1 over 16 plus 1 9. Let's see. It would then be 1 over 36 and 1 over 25, right? Now that's still the same total, isn't it? That's exactly the same thing. But that's the alternating version of the one above it. That does not satisfy the alternating series test because the numbers go up and down, don't they? If I take the absolute value, then this would be 1/4 followed by 1. That's not decreasing. 1 followed by 1/16 is, but 1/16 followed by 1/9 isn't. So this fails the alternating series test, but it still converges. Isn't that annoying? So if I pass the test, then I converge. But if I converge, I might not pass the test. I'm so glad I have that book online. Now, how do we know that that converges? There's another test we can do, and I promise I'll show you that one as well. But that's next week. Anyhow, that answers our previous question. Or my previous digression into weirdness. There's so much neat crap that goes on here. Somebody asked me another question. Go ahead, Jack. Number 20. 11, 3, 20. So let's look at 19 for comparisons. Sure. The thing that's messing you. Oh, okay. Well, let me just address that part. The reason it's n equals 3 is look at the actual term, right? 3n minus 4 over n squared minus 2n, right? The problem is the bottom. The bottom is n times n minus 2. So if it started at 1, when I got to 2, I'd be dividing by 0, wouldn't I? Oh, I have to move past 2 for this to be defined from everywhere on. So really, that's the only reason we start at 3, is because 2 is also up here. Sure. 19 says the integral from 1 to infinity n cubed over n to the 4th plus 4. So we're doing the integral test, right? So I just want to know whether or not I can find a function and figure out what's going on here. Place all the n's by x's. I'm going to assume that's the right function. Is that positive whenever n is bigger than 1? Is it continuous whenever we're bigger than 1? Is it decreasing? I think so. How do you know? It's a good question. But positive was obvious because that'll be positive, I'm adding. Continuous, it's never undefined because the bottom's always positive. Decreasing. Uh-oh. Let's look at the derivative. Derivative of the top times the bottom minus derivative of the bottom times the top over bottom squared. Now look at what happens on top. I have 3x to the 6th minus 4x to the 6th. Oh, if if I factor out an x squared, this piece is always positive. This piece is always positive. But this one, that's going to be negative once we get past whatever the fourth root of 12 is. And I'm pretty sure that, wait a minute, I know a fourth root. 2 to the fourth is 16, right? So the fourth root of 12 is a little bit less than 2. So this is less than 0 if x is bigger than or equal to 2. Oh, so it may not be decreasing from 1 to 2, but from 2 on it's decreasing. That's good enough. Now I just need to know if that integral converges or diverges. How do I do that one? That would only tell me what the limit is. It wouldn't tell me what the integral was. But knowing that the limit is 0, that's good. But is it going to 0, quote, fast enough? Because like 1 over x goes to 0, but that's an integral that diverges. My first reaction is due to u substitution. And then du is 4x cubed, which makes this 1 over u du, oops, there's a dx there, and a 1/4 out front. Wait a minute, 1 over u, what's my integral? A logarithm. 1/4 ln x to the 4th plus 4 from 1 to infinity. Let's put the limits part in, right? So this is the limit as t goes to infinity, 1/4 ln t to the 4th plus 4 minus 1/4 ln 1 to the 4th is 1, ln of 5. Dom, what happens to this ln? It's okay. All right. I need to know if this integral converges or diverges. That's a logarithm. As t gets bigger, ln does what? With the graph of ln, that's going up. This goes to infinity, so this diverges. So Jack, here, once I'd done the integral and found out that the integral test would work, you know, the integral diverges, my series diverges. The fact that we would do an integral from 1 to infinity versus 3 to infinity doesn't actually matter. Because that's just going to change this number here on the end. And so in this problem, where I can't start from 1, I have to start at 3, that just means your integral starts at 3. Perfectly fine. However, looking at that integral, my brain says that there's probably a partial fractions bit in there, and that's ugly. Because when I go back and I look at this, wait, I factored the bottom, that says partial fractions to me. Ew. When I go to do the integral, this integral is going to suck. On the other hand, yes, we can do the integral test. We also have, in the next section, the comparison test. So I could also try and look at these through that lens to confirm what we just got from the integral test, right? The integral test tells me this diverges. But I could also say, hey, let me think about this with the comparison test in mind. N cubed over n to the fourth, because when n is really big, the plus 4 doesn't do squat, right? That's really 1 over n, isn't it? So if I do the limit comparison test, and I get a number that's not 0 and not infinity, then those two things behave the same. And what do we know about the sum 1 over n? That's my harmonic series. It diverges. And now, Dominic, now I can do the limits because now I'm doing a comparison test. When I flip this over, that's going to give me an extra n on top. That makes that n cubed into an n to the fourth. That limit is 1. Wasn't that easier? I think the integral test should be a test of last resort. Way down there on the importance list. I can do it, but it really involves a lot. Comparison tests are a lot faster. Alternating series tests are a lot faster. Apologize to you all. I just had a very old movie flashback. How many of you have seen The Last Starfighter? Oh, I'm so old. The Last Starfighter. It's a very good sci-fi movie. Very weird. It is the first movie to use CGI. The CGI for that movie was done on the Cray supercomputer at Carnegie Mellon. So it's a local movie in that sense. Starship, one lone starship against a giant armada. What's this big button? Oh, that's Death Blossom. It's a weapon of last resort. Integral test is an integral of last resort. Don't use it. Go see the movie. That's your homework for the weekend. Watch that on YouTube. Anyhow, more questions. I know that movie's older than all of you, so why I didn't expect you to have seen it. Nora, you had a question when you handed it off to Jack. What's your question? 28 and 11.5. So this says approximate to 4 decimal places, right? 4 decimal places means you want the error to be less than 0.0001. So we're actually doing the same thing we did in problem number 24, but they didn't tell me the error explicitly. They just said 4 decimals. Does that make that easier? Hoorah. What else you got for me, people? It's an old movie. Which 36? 11,336. Please turn the page. 36. Okay, so the first thing it says is it says actually give S10, which means you need to add up the first 10 terms. And then it says to find an improved estimate of the sum. Beg your pardon? What do you mean an improved estimate of the sum? Well, box number 3 says that you can use the remainder. And that's a lower bound and an upper bound. So if you know it's between here and here, an improved estimate would be halfway between. And then part C is find a exact value, which is given in exercise 35, right there. So how close did you actually get? And if you wanted your error to be less than 0.1, 2, 3, 4 zeros and a 1, how many terms would you need to go out to? So it's really doing this integral. Now, I would actually think it would be very interesting to figure out how the hell he got this. There's a really neat paper on Euler's method for computing this sum. Just like up here, the 1 over n squared sum adds up to pi squared over 6. But what he used is a method that involves sums of sines and cosines, called harmonic analysis, which is incredibly powerful, but well beyond the scope of this course. Again, it's really cool, but it's not here. There is another course in which I can talk about this, but you'll notice he's called this zeta of 2, that Greek letter, and zeta of 4, right? That's that Riemann zeta function, the $1 million problem I was talking about. A lot of work on the zeta function. Leonard Euler was the late 1700s. Better? All right. So if you have questions about this over the weekend, you should be sending me emails. Otherwise, I will see you all on Monday, and we will talk about another pair of convergence tests that are even more powerful than the ones we've got so far. Have a wonderful weekend.